Good morning, good afternoon, or good evening, depending on where you are joining us from today. My name is Allison Jones, and I am with CNL Corporate Communications. Before I hand it over to CNL's Edward Azam to introduce Dr. Zablotska, I would just like to draw your attention to the Q&A function at the top of your screen. Throughout the presentation, we encourage you to type in any questions you may have for Dr. Zablotska, as we will have some great opportunity for question and answer following her presentation. We will certainly look to get to as many of these questions as possible following the presentation, which will end at 1 o'clock today. With that, Edward, I will pass it over to you.
Thank you, Alison, and warm greetings to everyone from Chalk River, Canada. It is my pleasure to welcome you to CNL's low-dose radiation research webinar series featuring world's leading researchers in the field of health effects of low-dose radiation. In this endeavor, we are pleased to have the support of Atomic Energy of Canada, the Canadian Nuclear Safety Commission, and Health Canada in these efforts. Today, it is my distinct honor to introduce Lydia Zablotska. Lydia holds the Salvatore Pablo Lucia Chair in the Department of Preventive Medicine at the University of California, San Francisco. She also holds an adjunct professorship at our own Carleton University in Ottawa, Canada. Lydia completed her medical and doctoral studies summa cum laude in Minsk and Lviv in her native Ukraine, and her doctoral studies at Columbia Mailman School of Public Health under the mentorship of the late Jeffrey Howe. Her research is distinguished for combining traditional epidemiological methods with advanced statistical modeling and new approaches to risk estimation and projection. For us, the community of radiation researchers, she has studied numerous cohorts affected by radiation, whether from fallouts, occupational exposure, or environmental contamination. She has studied both cancer and non-cancer risk, and the significant part of her studies has been on thyroid cancer and other thyroid diseases after exposure to radioactive iodine from the Chernobyl nuclear accident fallout in 1986. Lydia has been instrumental in recruiting large cohort studies in her native Ukraine and for biennial screening for thyroid diseases. She has had an illustrious career of service and mentorship. She has contributed to the works of numerous agencies, including the NCRP, the Canadian Nuclear Safety Commission, and the Radiation Research Society. Her work has been supported by numerous grants from the NCI and other agencies. She is involved in many academic teaching activities for which she has received the highest recognition. She is the recipient of the Golden Apple Award from the Schools of Pharmacy and Medicine at UCSF, and the very special Mentor Award for her commitment to the development and progression of early career investigators from the Conference on the Radiation and Health and the Radiation Research Society. Today, we are happy that she is joining us to discuss ionizing radiation and health, what we know, what we do not know, and the plan forward. Thank you, Lydia. Thank you.
Thank you very much, Ed, and to the Canadian Nuclear Laboratories for inviting me to give this presentation. It's my great honor to do it. Let me share my slides. Can you see my slides?
We can.
Yep.
Yeah.
Just wanted. Yes. Thank you. Thank you. So as Ed was saying, I would like to talk today sort of a general summary of radiation research, what we know, what we don't know, and the remaining questions. At UCSF, we have a Center for Radiation Studies, and our mission is to conduct radiation studies and to assess appropriateness of current radiation safety standards for various groups exposed to radiation through occupational and environmental exposures or radiation diagnostic procedures. And our goals to achieve our mission is to combine epidemiological methods with statistical modeling, but also advocacy work nationally and internationally. As Ed mentioned, I'm a member of the NCRP. I also work with various groups in the preparation of UNSCARE reports, and I contributed to several US National Academy of Sciences and reports, and recently started working with the US Environmental Protection Agency on the assessments of the risk coefficients for radionuclides. It's very rewarding to do all of this work, and a number of studies are now ongoing. So here I mentioned a number of studies in Canada. My dissertation was based on the Canadian nuclear workers. So since that time, I have a very special connection to Canada, and I continue working with researchers there on various studies, including a number of studies based on the Canadian National Dose Registry. We are also pulling together the data from Canada and other countries into the international pooled analysis of uranium workers and pooled analysis of uranium miners, where Canada also contributes. And finally, I've been working for a number of years on a Canadian fluoroscopy cohort study, which was initiated, my mentor, who was Canadian, and put this study together at the end of 1970s. And I continue on studies in former Ukraine, Belarus, and Russia, working with uranium processing workers and people who were afflicted by the Chernobyl accident. I know it's customary to put the thanks to your collaborators at the end of the presentation, but because this is such a important summative talk, I wanted to introduce you to our Center for Radiation Studies, and these are the students and colleagues who are working with me on many projects. Not pictured here are a number of students from Canada with whom I collaborate. These are the students that are working with Dr. Professor Paul Villeneuve at Carleton University. And so he has a number of students at Carleton, but also at McGill that are working with us on radiation studies. So I will mention today very briefly what radiation is, and I will talk about methods of studying radiation, primarily juxtaposing risk projection and empirical direct studies, and then present two case studies, one on nuclear workers and one on diagnostic imaging procedures, and then summarize the remaining questions or knowledge gaps and our plans and proposals for moving forward. So many of you may be familiar with radiation, some of you may not be. So for the benefit of everyone, I just wanted to have a very brief summary of what radiation is. Radiation is energy, could be expressed as energy, as electromagnetic waves, or as moving subatomic particles, especially high energy particles that cause ionization. It's divided into low energy and high energy radiation. On the left, you see sort of a depiction of waves, and on the left, with shorter distance between the waves, is ionizing radiation, and the nuclear energy is going from right to left, increasing. And then there is the second graph, which going on an opposite direction. So you will see in the middle is a visible spectrum with the colors, and then the ionizing radiation is in the right. Ionizing radiation here, so it's types such as gamma rays, X-rays, or alpha particles. There are multiple routes of exposure. People could be exposed through inhalation of particles, ingestion, or direct irradiation of the whole body or parts of the body. The total injury depends not just on the dose of radiation, but also the speed or rate with which the dose was delivered, which is frequently called dose rate. Also important is the percentage and region of the body exposed, as our tissues and organs have different radiosensitivity. This picture shows that different rays and particles have different penetration rates. So very heavy particles could be stopped by very simple measures such as paper. Gamma rays only could be stopped by lead, and they go through the body unimpeded. In the past 30 years, the International Agency for Research on Cancer has evaluated the cancer-causing potential of more than 900 likely candidates, placing them in one of the following 4 groups. And the first group is where the ionizing radiation, X, and gamma radiation is currently placed as the most carcinogenic to humans. Radiation effects of the ionizing radiation could be placed into 2 broad groups. Deterministic effects, which are above some particular threshold, and this is where low LET whole body exposure is above 4 gray. And the severity of the observed health effects depends on the dose rate or how quickly the dose was delivered. Stochastic effects, these are the ones that I'll be talking today, occur at low to moderate doses. There is no threshold, meaning that even small doses cause an effect. And then the severity of the effect is not affected, but what is affected is the probability of this event or health effect in the population. The higher the dose to which the population was exposed, the higher the probability of the adverse effects. This simple graph shows the effects or the mechanism of radiogenic damage to help us understand how radiation leads to short-term and long-term health effects. Short-term effects are based on the immediate effects to acute exposure, which could be cell killing, tissue and organ damage, and even death. And then late effects are showed by damage of the nuclear material, DNA mutation, chromosomal aberrations, which could lead to malignant neoplasm or hereditary genetic disorders. This is, of course, was a very simplified version of what is happening at the biological level, at the molecular level. There could be many, many other responses, as I show on this graph. For example, when we talk about cellular responses, we could talk about radiation gene activation, protein production, altered signaling, cell killing, and tissue disruption. So these processes are extremely complex, and we don't fully understand all of them. I will be using a lot of different quantities today to describe the effects. I'll be talking about absorbed dose, effective dose, equivalent dose, and dose rate. I already mentioned what dose rate is. It's the speed with which the dose is delivered. And then absorbed dose is the amount of energy imparted to the mass or to the organ, with the dose below 100 milligray being a low dose exposure. And then equivalent dose is particular particular quantity where we look at the way we use radiation weighting factor, and it is used to compare different types of radiation, for example, X-rays and gamma rays. And then effective dose is an equivalent dose that has been averaged over all organs and used for biomonitoring. So you'll see in studies of nuclear workers, we frequently use effective dose expressed in millisieverts. In the United States, we have this data from the EPA showing that the majority of exposure to the general public is coming from the radon and background radiation. but the part of the computed imaging radiation is coming up. This is the blue one on the pie chart. The contributions of others are marginal, but are growing, particularly from a nuclear medicine. In this graph, I was trying to show that as the radiation increases to different groups of people, the number of people at risk is decreasing, so they're going in the opposite direction. General public has an annual limit of 5 millisievert, and as recently as 5 years ago, that average dose was in the US about 3.6 millisievert, and 80% of that was due to natural sources such as radon, less than 1% due to occupational exposure, and about 20% to medical procedures. So going back to the doses to the general public and 20% for medical procedures, I wanted to show you very powerful numbers. If you look at the 2004 data from the US, there were approximately 962 X-rays per 1,000 people per year. So almost every individual on average had one X-ray that year. Attributable risk percent for leukemia from just the X-rays in that year was 0.9%, meaning that from that exposure alone, the risk of the outcome in the exposed would be almost 1%. And imagine that this is adding up through the years and some people having many more X-rays. In 2007, for example, there were 72 million of scans, CT scans per year in the United States, which alone would be responsible for 2% of cancers. The numbers were growing exponentially. And in 2011, just 4 years later, the number of CT scans in the US was 85 million. This caused a tremendous concern in various radiation research groups, and a number of policy measures have been undertaken to reduce that number. And since then, it went down, and as recently as 2016, it was still going down, was dropping to 76 million. Right now, the average number of CT scans in the population in the US is 279, and it is about 60% lower in Canada at about 144 per 1,000 per year. There are various dose examples here showing from top to bottom. The highest ones are coming from galactic rays, occupational exposures going down to very little minimal exposures from flying. But what I want to sort of put the ionizing radiation exposure scenarios in perspective is this is the graph which shows the radiation levels. You see the spikes on the left in March of 2011 when there were fires at the Fukushima nuclear power plant. So we see these spikes, these high levels of radiation going up to about 12 millisieverts per hour. That puts you into perspective in these other scenarios on the graph, where you look at whole body CT has almost similar spike. So when we talk about occupational exposures, we also need to remember that exposures from imaging are on the same scale. They are pretty large, and I will try to get to that today. So there are two methods to study health effects of radiation. We could do risk projection methods. That's where we use the data from the influential study of atomic bomb survivors that provides sort of everything, almost everything we know about radiation effects. An advantage of that is that we have a great statistical power and precise confidence intervals of the risk estimates in the A-bomb survivors. Disadvantage is that we need to extrapolate from the population that was exposed to gamma radiation in 1945 to, for example, current day situation in Canada with CT scans. So it's a different population, different time, different scenario, and also different type of radiation from gamma to X-ray. A better way of doing this research will be to do empirical studies where we actually collect the data in Canada and follow people up and examine their risks. This will be a very laborious, long undertaking, and you will need very, very large groups of people to get any estimates with statistical significance. So today I present two case studies. The first one is a quick summary of what we know from the study of atomic bombings in Japan. Immediately after the bombings, there were people who died from exposure, burns, and radiation effect, immediate effects. We are estimating that between 90,000 and 140,000 people died in Hiroshima, and about between 60 and 80,000 in Nagasaki. 20 years after the bombings, there were deaths observed, and the lifespan study was formed, which included 87,000 people. The mean dose in the cohort, these were the people that were within the epicenter of the explosion, included the dose was about 110 milligray and ranged from 0 to 3.5 gray. And the only significant consequence at 20 years with regards to health effects was the increase in cataracts, leukemia, and thyroid cancer. So these were sort of original indicators of radiation exposure. 10 years later, there was a significant increase in solid cancers. And then at 50 years after the bombings, there was an unexpected increase in non-cancer diseases. Solid cancers were about more than 10,000 in this cohort, but crucially, less than 5% of observed solid cancers were due to radiation. And in leukemia, 93 out of the 296 were due to radiation. So this shows you that as the cancer incidence progresses with age, not every cancer in the exposed population is due to radiation. And we need to do careful studies to sort of separate the baseline or age-related cancer rates from the ones due to radiation. And then at 65 years, this is the follow-up that ends in 2009. This is the latest follow-up that we have. We have sort of new developments. First of all, about 25,000 people who were not in the city were added to the study. The new dosimetry system, DSO2R1, has been developing. And because we are including people who are not in the city and that have no radiation exposure, the mean dose has dropped. So now it's about 15 milligray in Hiroshima and 2.5 milligray in Nagasaki. The distribution, of course, is very distorted. A number of people had very high doses, but we have about 25,000 people who have no doses. Solid cancers continue to be observed, and by the end of 2009, there were more than 22,000 cases. But the percentage of those due to radiation has been holding steady. It's been estimated at 4.4%. Leukemia and thyroid, those original cancers, now form only a small fraction of the accepted radiation burden. And what's very interesting is that now we're observing non-linear shape of the dose response, particularly for solid cancer in males. And what has emerged as a very important issue is that there are significant differences in risk between males. Leukemia has the highest risks, such that people who were exposed to 1 gray of radiation after the bombings have a 5.6 times higher rate of leukemia during follow-up compared to those who had dose 0. And here is a study, the latest sort of summary of all the studies from the ABOM studies. And you could see the two outcomes highlighted in blue. So lung cancer is the only significant cancer where we see a significant difference in risk between males and females, both for incidence and mortality data. All others are not statistically significant, and we are looking at esophagus, stomach, colon, liver, kidney, bladder, and thyroid. But we see a sizably higher risk in females compared to males. The only sort of the outcome bucking the trend is the colon cancer in females, colon cancer incidence where the risk in males is higher than females. All other numbers in the table are showing a definitive trend where risks estimated for females are higher than for males. So getting to our case study, who is considered a nuclear worker? What is occupational exposure? There are many types exposure. There could be occupational exposure, public, medical, emergency workers, non-human biota. UNSCEAR defines the occupational exposure as having 6 broad categories. And the first one is the nuclear fuel cycle. And then there are other ones that are involving medical uses of radiation and industrial use. Today, I'm concentrating on the workers of the nuclear fuel cycle. The process starts with uranium mining and then milling of the ore by crushing and grinding to liberate the minerals, and then leaching them with sulfuric acid to dissolve the uranium oxides. It later goes to uranium processing, conversion, refining, and the use of the nuclear fuel for electricity manufacturing, and then storage, reprocessing. So today I will be mentioning workers who are involved in the production of nuclear energy, manufacture of weapons, enrichment of the processing nuclear fuel, and reactor and weapons research, but I'm not including medical or dental workers or underground miners. To give you sort of an idea of how many people are affected, between 1995 and 2002, there were about 23 million monitored workers around the world. Most of this is coming from natural sources, 57%, and that includes non-uranium mining or coal mining, which also has some exposures. And then there are man-made sources of radiation, and this is about 660,000 workers working in the nuclear fuel cycle, and includes about 34,000 uranium miners. So why should we study nuclear workers if we want to know the effects of low doses of external radiation? The reason is that their exposure is very carefully monitored and the data collected. The dose estimate obtained from personal dosimeters that are worn by the workers. These carefully collected doses will help us provide a direct assessment of risk at low doses and help us estimate the accuracy of current risk estimates, and also assess whether atomic bomb survivors' data is appropriate to monitoring the data to establishing public policy standards. The problem, of course, and there are numerous, is that the studies of low dose exposures have very low statistical power, and I'll talk about it a little bit more. So, just to summarize, what we want to know are the effects in the low dose range, both for occupational exposed workers who have a limit set at 50 millisievert a year, and also for the public, where the limit is set as 5 millisievert a year. So we want to know low dose exposures. However, the current risk estimates, which are based on the A-bomb study, are driven by the people in that cohort who had high doses of more than half a gray. So what do we do about that? We could use risk projection, as I mentioned. So we could use the data from the A-bomb study and apply it to the doses of nuclear workers and general public to estimate the risk. Or we could do empirical studies or direct studies and of the nuclear fuel cycle workers. So a number of these have been published, and a number of them are in progress, the pooled analyses. The BR7 committee, or Biological Effect of Ionizing Radiation, Committee 7, Phase 2, sort of summarize the results as they were published until 2006. And this is sort of our current guidance summarized by a committee of experts, which says that the risks of leukemia in ABOM survivors are about 10 times higher per unit of dose compared to all cancers. Then nuclear workers, based on these pooled analyses, showed the same results, but their risk seems to be half of those observed in the ABOM study, or a dose and dose rate effectiveness factor of 2, where we divide sort of the effects by 2 observed in the ABOM. So if we want to extrapolate the from ABOM study, we have to use the estimate and halve it by 2 to project the risk to nuclear workers and the committee summarized the evidence that was published up until 2006 by saying that the estimates are lower in the occupationally exposed workers are lower than the linear estimates obtained from studies of ABOM survivors, but compatible with a range of possibilities. They also said that the evidence does not suggest that current radiation risk estimates for cancer at low levels of exposure are appreciably in error. But they acknowledged that there was a very wide confidence interval of estimates. And they concluded that the occupational studies at the time were not suitable for the projection of population-based risk, and that policymakers should continue using atomic bomb survivors to project the risks to occupational exposure. Since the BR7, a number of studies have been published, and here I show just some of them, the most influential and the largest ones. And the ones highlighted in blue are the studies that have actually pooled the data from a couple cohorts. Like, for example, the study from the UK is a national study from various uranium processing and nuclear generation cohorts. You see that the numbers here are numbers of working rivaling those numbers that we have in the ABOM study. And the estimates still are not statistically significant, primarily because the mean doses, and that the third column from the right, are very, very low, with the exception of very few studies such as MAIAC, where the doses are sort of not low dose, but are approaching those in the high dose group in the ABOM study. So we see from this slide the limitations of individual studies. They have insufficient power for internal analysis because of the small number of deaths or small effects due to small exposures, small doses. Many of the occupational studies don't have adequate information of lifestyle factors, which could serve as potential confounders. There are measurement errors in dosimetry. There is variability in reporting thresholds, and these thresholds also changed in many countries in different ways over time. The dosimeters that the nuclear workers are wearing are measuring the total body doses, but while what we are interested in projecting risks is to know the organ doses, and they're not the same. And finally, many of the studies is based on cancer mortality and therefore are liable to misclassification of causes of death. In this slide, I just want to show you why it is so hard to get adequate data from direct observation of nuclear workers. In this slide, you see the US Nuclear Regulatory Commission data on workers annual, and you will see that 99% of workers had the doses below 2 rem. So it's very, very low exposure. So what do we do in this situation? Our answer is to do pooled analysis of occupationally exposed workers, and it has pros and cons. We could obtain larger population and have a more precise estimate of risk due to improved statistical power. And we could also try to understand the differences and similarity between different cohorts that are contributing to the pooled analysis. The cons is that there's still low level of exposure, and there could be also mixing of exposures because many cohorts are exposed not just to gamma radiation, but they also have other exposures to internal emitters and particles. So some of the examples of these pooled analyses are 15-country study, INWORKS, the UK study from the National Registry of Radiation Workers I mentioned previously, and of course the Canadian National Dose Registry studies. There are some limitations of these pooled studies as well. First of all, is that there are possible biases. When you combine biases in individual studies together, you get a multiplication. And there could be errors both in exposure assessment and in outcome data. As I mentioned earlier, there are different thresholds for recording. So when you combine the data, you have to deal with that. And inadequate adjustment for confounders remains. And then there could be also an association between cumulative dose and mortality from smoking-related cancer. So we need to carefully look what are we analyzing, and if there is no data on smoking, we shouldn't be including smoking-related cancers in risk estimates. I mentioned the 15-country study, which was published in 2005 and 2007. This is a study of more than half a million workers, which included actually 19 cohorts for 15 countries that are listed on this slide. They had a very carefully designed a priori protocol with selection criteria. They tried to collect data on confounding, socioeconomic status. Smoking was not available in the majority of studies, so they used indirect assessment of smoking. So in the end, they had to exclude a number of people because they did not have information on socioeconomic status. And the final population for analysis was reduced to 407,000. If you take a look at the slide, here is the 407,000 workers, and the mean cumulative dose over all occupational career for the workers from these 15 countries was 19 millisievert. Very, very low dose. The summary of the results from that study is that it was a very strong, healthy worker effect, meaning that people, to stay in the industry, they had to be healthy. And so when compared to the general national population rates in their own countries, workers had lower mortality. However, when the analysis was done according to the radiation dose they received during their occupational career, there were significant increases in risk for lung cancer and multiple myeloma. But I want to point out that was 2 significant out of 31 tested. There was some other no increase of leukemia and little evidence for relationship from non-malignant diseases. The thing that the issue that attracted a lot of attention was the effect of contribution of Canada to the study. You see on this graph that all of the countries has their risks closer to 1, and then there's Canada way over there with an estimated risk very high. And so 15-country study published the estimate as close to 1 per sievert, but when Canada was excluded, the risk was decreased by more than 40%. What's going on here? This was actually the data that was contributed to the 15-country study was based on my dissertation, and I did not observe that effect. The estimate was high, but it was not significant. So I spent 10 years after my dissertation trying to untangle this with my Canadian colleagues from the Canadian Nuclear Safety Commission. And in 2014, we published this study where we pointed out that it's very important how you do pooled analysis. And although the 15-country study was done very carefully, one of the selection criteria that studies had to have socioeconomic status resulted in very unusual results for Canada. So here you see, my study showed not significant effect. Then pooled analysis, 15-country study showed 6.6, tremendously higher risk. And that's primarily because 15-country study excluded almost 30,000 workers from nuclear power plants such as Ontario Hydro and others, but retained the workers from Atomic Energy of Canada Limited. These were early workers with higher exposures compared to nuclear power plant workers, and they had socioeconomic status, so they contributed much more data. In this graph, I'm highlighting in blue boxes the most important findings from our 2014 paper, and we are showing that if you look at the 42,000 plus workers in Canada who were monitored from 1950 to 1999, we see that there is absolutely no increase in solid cancer. It's a negative estimate. But the 3,000 workers from AECL, only early workers, those who were employed before 1964 and had slightly higher doses, they have a higher risk. And they're the ones that pulled the risk estimate for Canada and for the whole 15-country study, essentially making their risk estimates very probable. So because of that, a new study was initiated, which included UK, US, and France, and it's called INWORK study. And this is our latest and largest pooled study of about 300 workers who also had very low doses, mean cumulative doses gray. And here you see the estimates of risk for cancer and other outcomes. And also for leukemia, of course, much higher for leukemia and order higher compared to the solid cancer. There were also a significantly increased risk of mental disorders and circulatory diseases. So now in one slide, I want to compare ABOM survivors on the right, INWORKs in the middle, and 15-country on the right. And what probably jumps out at you is that the estimates in the INWORK study for solid cancer are actually higher than they are for ABOM survivors. So these data that we see here show no justification for dividing the risk estimates by 2 when projecting the risk using ABOM data. So this direct estimates is telling us that risk projection method should be done very, very carefully because we don't see attenuation of health effects with risk projection, risk protraction. So in summary, we see that risk estimates for occupationally exposed workers are much closer to the ABOM study, and there was no apparent difference between the effects of instantaneous and protracted exposures. So what else did we learn for workers exposed to low doses? We learned that when we extrapolate from high doses to low doses, we have to be very careful. And when we are pulling the data, we have to be even more careful. There are also some very big caveats. We need to consider that there still may be socioeconomic status effects, healthy worker effect, duration of employment, smoking-related cancers. Also, typically, nuclear worker studies exclude women because there are so few of them in individual cohorts, and many of them do not collect information on race. And both of these 2 factors have been shown recently in the other studies to have an effect on risk estimates. So we have to be very careful when doing both risk projection studies and direct observational studies. So based on this data, the NCRP recently concluded that ionizing radiation is a definite carcinogen, but a relatively weak one. Epidemiological studies are insufficient to estimate risk at very low exposures at several milligray, but are now much better to estimate risk from about 50 to 100 milligray. Radiation biology is very helpful to understand the processes that lead to health effects. And there is no threshold effect. And there's probably linearity of the effects, but we need to continue looking into this, as definitely non-linear effects have emerged in the most recent follow-up of the ABOM survivors. So we have a number of upcoming studies looking at uranium miners, uranium processing workers, and a new and very interesting 1 million-person study of atomic veterans in the US led by Dr. John Boyce. The IPO study that is being funded by the Canadian Nuclear Safety Commission will be the first of its kind. There have never been pooled analysis of uranium processing workers. These are the workers that are exposed both to external and internal radiation by uranium products. And so we have about 16 cohorts, and working with our collaborators at various Canadian cohorts, and the results are expected perhaps in 2 to 3 years. And the MPS study has published a number of studies this April for Manhattan Project and Atomic Veterans, and a couple more primarily uranium processing workers studies are coming. And then after publishing individual studies, they will be pulling them together and analyzing about 1 million. Very quickly, the second issue is the CT scan studies. In this slide, I summarize to say that we know quite a bit about risks of high dose exposures, the first 2 columns. And we know quite a bit about occupational exposures. But the last column, diagnostic X-ray examinations, you'll see that for many outcomes, we say no studies, no studies, no studies, or evidence is not sufficient. So this remains, sort of like a very glaring omission. We have millions and millions of people having a very large number of CT scans with doses comparable to some of the occupational exposures, yet there are no studies of this particular type of radiation and this particular type of. And these exposures are very similar. So here I'm showing that the whole body CT scan, just one, produces a dose of about 16 milligray to the whole body, which is very comparable to the mean dose for nuclear workers that I was showing you of about 19 in the INWORK study. So this is with respect to bone marrow and associated hematologic source, but the same is very similar to lung doses. Again, chest CT scan produces the mean dose of about 6 milligray, sorry, not 66 milligray of chronic X-ray exposure, which is very comparable to the nuclear workers in many different studies that have been observed. The first studies of CT scans have been published, and the first one was in 2012, coming from the UK. These were studies of children. They're the most sensitive to radiation, and they were followed for a short period of time, and significant effects were found for leukemia, as shown here, and the effects were very high, magnitudes of order higher than risks observed in the ABOM study, and also for. And in this graph, you could see the results from the UK study, and you'll see that whatever category dose, the risks are high and significant. There was a larger study, but was less sort of accurate dosimetry based on 680,000 children from Australia. And since then, there have been a number of studies published, 10 studies published in Europe. So what do we know now about the effects of CT scans? We need to consider the effects of underlying condition, and 2 of them are reverse causation and confounding by indication. Reverse causation being that perhaps children had leukemia or brain cancer, and that's why they were getting the CT scans. And confounding by indication could be that the children had some other disorder for which they received the CT scans, and that disorder is also connected to leukemia. So for example, children with Down syndrome frequently could have injuries, and then they have CT scans, but they also have the higher risk of leukemia. So if we were to look at these and account for them, that probably will reduce the risk estimates we see from CT scan studies. Also, in the last 15 to 20 years, the doses from CT scans have been sort of moderated, and prescription patterns have changed, and physicians are now much more careful in referring children for any reason to CT scans. And also, we could have longer follow-up to sort of assess So to summarize, our knowledge gaps is that we don't know the effect of protracted exposures. We thought originally that the effects of protracted exposures will be about 50% of the same dose delivered acutely, but occupational studies do not support that. We don't know the relative biological effectiveness of various types of radiation. We know it, but some biological studies are giving us suggestions that X-rays are actually much more harmful than gamma rays. The shape of the dose response is not known, and as ABOM studies are saying, it's different in males and females. And we don't know the shape in the low dose range. We are not sure if there is a threshold at 5 or 10 or 20 milligray below which there is no risks. So it could be a shape shown here. We don't know the effect on different types of cancer. We also are not accounting for genetic and lifestyle differences between different populations. And we don't know the differences in mechanism of radiation damage at the cellular responses. How do we address these problems? We need to do pooling of studies. I think I convinced you that pooling is important, of studies of people, not just doing risk projection studies. We need to incorporate gene environment interactions data, and we need some improvements in measurement, especially in the low dose range. And some of this we are hoping to do with our Canadian fluoroscopy. Have a lot of measurements. One of the cool projects that I recently completed is that based on radiation, is that women and men have a different risk of lung cancer. Because of this, in the ABOM study, women were not allowed in the US to start training for the mission on Mars because they would have exceeded the dose, allowable dose. So the committee that was formed by the National Academy of Sciences will call Space, Radiation, and Astronaut Health. And I was privileged to be part of that committee where we reviewed the evidence and said that right now, there's only one study, ABOM survivors, that is showing significant differences in risk of lung cancer between males and females. It's important, but other evidence does not support it. And so based on that, women should be allowed to train, and they could do it. So women started training for them. So I want to thank and conclude with this slide showing my collaborators, various institutions in the US, Canada, Ukraine, and other places. Thank you very much for your attention.
Thank you.
Are there any questions?
Oh, yeah, sorry. Thank you, Dr. Zablotska. We do have some questions that I will put forward to you. The first one is the only problem with the direct method example given using diagnostic cohorts, statistical power, for example, problems of reverse causation?
No, there are other parts. One of the problems with direct observations that are low doses, right? So we're observing either occupational exposed work or CT scans where individual doses are low and cumulative doses are low. And with low exposures, we're expecting low risks. So for that, we have to have millions of people and follow them up for a very long time. So that's why there are some other issues. So it's not just reverse causation or confounding by indication. There are many other issues.
Okay, another question. Are there problems in comparing LSS and nuclear worker studies? For example, effects of the differing underlying populations and also the radiation energy, much higher energy for LSS.
Absolutely. That's exactly what I was trying to show, that projecting the risks from the population in 1945, start from the war, of different genetic makeup, projecting the risk from that population to the people who are exposed to X-rays from, for example, imaging procedures is really problematic. The rates of smoking were very different at the time in Japan and smoking now. The risks of other confounding variables are very different. And we are seeing the results of that. As I showed, the actual data from combined nuclear worker studies do not support the halving of the effects when we move from acute scenario to chronic exposure. And so we have to be very, very careful when we do these risk projections. But mind you, all of our risk limits that are being used by public policymakers are still based on A-bomb survivors. So we need to sort of gather more evidence and try to persuade the policymakers that the time has come to use other supplementary data from other studies of direct observations.
Okay, another question. In recent in-work study, and how much contribution from internal and external doses, which would decide type of cancer incidence?
So the recent in-work study tried to exclude people with neutron doses and primarily included nuclear workers who were exposed primarily, again, to gamma radiation. So that study does not include uranium processing workers, for example, that could be exposed to substantial doses from internal emitters. They also tried to look by eliminating the outcomes that would be connected to internal emitters, and that would be lung and liver. So I think they tried to do as best as they can with available data, but there's still the possibility that some of workers had both exposures, external and internal.
So you noted that there is an increase in the annual dose to the general public in the US. What do you attribute this increase to? And is it due to increased diagnostic radiation exposure?
Yes, that's what the data is showing us, that in the last 2 decades, the rise in the annual dose to the general public from background radiation is primarily from medical procedures. And this is connected to the rise in CT scans in particular, but fluoroscopy procedures are also important.
So as a physician, how do you balance potential radiation risk of medical imaging with the benefits resulting from diagnosis and treatment of disease?
That's a very good question. Although I do not treat patients currently, but I am trained as a physician and work a lot with educating medical students, and this question comes up very frequently. CT scan is a wonderful tool that we have in our diagnostic toolkit, and so we should be using it in a very balanced manner. We shouldn't be refusing to use it because it is the best tool available for many diagnostic problems that we have in front of us. What we have to remember is that assess the risks not only on a scale per radiation dose, but we need to see the risk from procedures. So what I like to look at that is to look at the absolute scale. And what we know from CT scan studies is that right now we are saying per 10,000 scans that have been done, the risk of increased, for example, brain cancer would be about 6 per 10,000 CT scans. So that gives you a perspective a little bit better than just looking at the relative risk per unit of radiation dose. And if you know that, and then you see a patient who really needs the CT scan, you will balance that 6 per 10,000 patients with the perhaps very lethal disease that you're trying to rule out.
Okay, thank you, Dr. Zablotska. I think that's unfortunately all we have time for today. I'll just ask Dr. Azam to join our screen again.
Thank you very much, Lydia, for a wonderful, wonderful, informative webinar. We really appreciate it very much. And I know it's being recorded and it will be available for many to listen to later. I will certainly be listening to it over and over again. Thank you, Lydia, and see you all on our next webinar, upcoming webinar. Thank you and have a great day. Thank you, Lydia. Thank you.
Thank you very much.